Hey, what's going on, guys? Today we're going to go ahead and discuss work. This is chapter 6, section 4. So to start things off, let's define what work is. So work is just the ability of a force that needs to be applied to move an object a distance or displacement. Displacement just means moving an object from point A to point B. And a force just means how much force needs to be applied to get that object to be moving. Okay, so another equation that we're going to kind of need besides work is force. We need to define what the equation is for force. So force is equal to the mass of the object times the acceleration. And the acceleration of the object is going to be due to gravity, which is a constant. And that constant is 9.8 meters per second squared. Another one that I would suggest that you would memorize is DMV, or density equals mass over volume. Just because you're going to be given a mass, and later on we're going to go ahead and have to use that mass to go ahead and we're going to be given a volume, and we might be given a density, and we're going to have to use that to calculate our mass to plug into our force equals mass times acceleration formula. And we can go ahead and manipulate this formula and make it look like, because sometimes we're going to need to find out what our mass is, and mass is equal to density times volume. Okay, so like I've always stated, the best way to look at these things to apply them to examples. Here's a small little quick example that we can go ahead and work on first. So find the work done in moving a 10 kilogram object 6 meters from its initial position. Okay, so since what do we have here is a mass, and we know that force equals mass times acceleration. We know acceleration is a constant, which is 9.8. We multiply that by 10, which is our mass. That should give us what our force is, which is 98 newtons. Okay, now that we have our force, the question is asking us to find the work done. So we know that the formula for work equals force times displacement. And displacement is just how much an object moved from its original position, which in this case was 6 meters. So you know that this is 6, and our force was 98, which equals the work. So that means work equals 98 times 6, which gives us 588 joules. And another way to write joules is just Newton times Newton meters, Newton times meters. So that's how much work needs to be done to move a 10 kilogram object 6 meters from its initial position. Okay, so let's go ahead and look at another one. And let's start getting into some of the more applicable problems. So, example number 2, we have when an object is x feet from the origin, a force of x squared plus x pounds acts on it. How much work is done in moving the object from x equals 1 to x equals 3. So, the general formula of work, we can go ahead and use an integral. So, work is going to be equal to the integral from A to B, which is going to be the place that we're moving it from, which is the initial position, to the final position. And here we're going to have our force, and it's going to be a function of force in dx, meaning we're going to go ahead and take small little cuts of it, or small little pieces of it, and we're going to go ahead and add them all together. That's what the integral is used for. So in this case, we know that a force is given by this function here. And we know it's a force because it's given in pounds. Pounds means that it's not a mass, it's a weight. When we have a weight, that means acceleration is already taken into consideration. So our work is going to equal to A to B of our function, which is going to be x squared plus x dx. We already have everything in respect to x's, and we know that we're moving it from x equals 1 to x equals 3. So we know that x equals 1 is our A, and x equals 3 is our B. So our work is going from 1 to 3 of x squared plus x dx. So we can go ahead and plug this into the calculator if you have an integration button, but if you don't, I'll show you how to do that right now. So our work between 1 to 3, actually, let's go ahead and jump a step on that. We're going to go ahead and take the antiderivative of that, because that's what we need to do to go ahead and get the integral out of there. So if we take the antiderivative of that, it's going to be x cubed over 3 plus x squared over 2. And we're looking at it through 1 and 3. Now we got to go ahead and use f of b minus f of a. And we go ahead and plug that in. Our 3 cubed over 3 plus 3 squared over 2, which is our f of b, minus 1 cubed over 3 plus 1 squared over 2 is our f of a. And that should give us that the work is going to be 38 over 3 foot-pounds. So the work needed to go ahead and move that object of a force that is ever changing from 1 to 3 is going to be 38 over 3 foot-pounds. Alright, so let's go ahead and do another example. So the next example is going to be a rectangular tank with dimensions that we're going to go ahead and have to pump out. So we have a rectangular tank with dimensions 5 meters by 8 meters by 3 meters. It's filled with water. Find the tank using a pump placed 4 meters at the top of the tank. So in this problem, I'm going to give you the water's density is 1,000 kilograms meters cubed. So this is something that's a little more applicable to the science field. So we want to know how much work is going to be needed to be done to pump out water out of a tank with those specific dimensions. So first thing we want to do is go ahead and draw this out. So we have a rectangular tank. And this tank has a spout that is 4 meters high. Well, we know that this is a 5 by 8 by 3. Okay. And we want to go ahead and find out what the work needs to be done. So what we're going to do is we're going to go ahead and, as we did in other problems, such as when we were finding the volume, we went ahead and cut it into bite-sized little pieces. We're just going to take one little slither of water and turn it into a cross-section. So if we go ahead and draw that out, our cross-section is going to be like this. Right? So our cross-section has a thickness which is supposed to be very, very, very small. Okay? And depending on how we draw it, that'll depend on whether we use dx or dy. Alright? So, but we know that this is always going to be 5 and this is always going to be 8. Now, so what we're going to have to go ahead and do is we're going to go ahead and we're given the density. So we'll go ahead and use the mass is equal to the volume times the density. Now we know that the mass is equal to volume, which we know the volume of this, and this is going to be the mass of the slice. We know the volume of the slice is equal to length times width times the height. So the volume is going to be equal to the length, which is 5, or 8, sorry, the width, which is 5, and the height, in this case, depending on how we draw it out, it'll be, but as you can see, it's horizontal. So let's go ahead and draw out how it'll look on our graph. And you always try to go ahead and put it near the origin. So we know that this is 4 feet. We know that this is 3 feet. And we know that this is 5 feet. And that cross section is right here. Right? And what we know about that cross section is that this little part is a y value. Okay? That's what we know about that. So, since our cross section is perpendicular to the y-axis, our height, our thickness of that is going to be dy. So if we go ahead and multiply that, our volume is going to equal to 40 dy. Okay. Now we go ahead and plug that volume into our mass formula, and we have 40 dy times our density, which is 1,000. Our mass is going to equal to 40,000 dy. Now that we have our mass, we can go ahead and input that into our force formula. So our force is equal to mass times acceleration. And we know that our force is equal to 40,000 dy. And we know that our acceleration is a constant, which is 9.8 meters per second squared. You go ahead and figure what that is, and that gives us 392,000 dy for our F. Now, we're trying to find the work. And what we did is we went ahead and cut this water slice into a very, very fine slice. That's what is dictated by our dy. So our force is 392,000 times dy, which is our thickness, right? But that's not our displacement. We need to go ahead and figure out displacement. And that's why I said it depended on how you drew it out. So on our graph, this graph here, our displacement is how much does the water need to move through it. So the whole thing, which is 4 plus 3, which is from the top to the bottom, is 7. But we have a y here. So our displacement means that this water slice needs to move 7 minus y. Because that's whatever the bottom of that slice was, is some type of y value. But we know the whole thing is 7. So we know that the area from here to here is 7 minus y. So that's going to be our displacement for what our water slice needs to move. So our displacement is going to be multiplied by, or our force needs to go ahead and be multiplied by which this is our force, needs to be multiplied by our displacement, which is 7 minus y, which is our displacement. So now that we have that, that is the work done to go ahead and move that slice. But the thing is, we need to go ahead and see how much it'll take to pump out all of the water. So not just that slice, the slice above it, the slice above that one, and above that, all the way till it reaches the top of it. But not only that, the slices below that. So the work needed to be done. So for whatever slice we decide to choose, how much work needs to be done to go ahead and pull out all of the water. So we're going to go ahead and use an integral. So our work is equal to integral of, and in this case, each slice is moving from this area to this area. The slice cannot fit through here. The slices only go through here. So the work needs to be done from 0 to 3. And then we go ahead and input the rest of our work formula into there. So we have our force, which is 392,000 dy, times our displacement, which is 7 minus y. And we go ahead and input that into our calculator. And we're going to get that the work needed to move all of the water, or to pump out of the water, is 646,800. So the amount that it needs is 6,468,000 of work needed to be done to go ahead and pump the water, or to pump out the water. So what does that mean? That means that every single slice in there, to go ahead and pump it out from 0 to 3, we need about 6,468,000 of work that needs to be done on the tank to empty it. Right? So that's how you can go ahead and solve that problem. Now what we can do is we can go ahead and solve another one. The thing is, not all tanks are built equally. So the thing is, even though in this one we were able to use the volume of a rectangle, which was length times width, it's not always going to be the case like that. Sometimes you might get different shapes, different types of containers. Some might be cylindrical, some might be conical. There's many different types of shapes of tanks. So another example that we can go ahead and do is we'll do conical. So example number 2. So a conical tank standing on a vertex standing on its vertex has a radius of 10 meters and a height of 20 meters. The tank is 1/4 full of water. Find the work needed to empty the tank using a pump placed 4 meters above the top of the tank. Okay, we're going to go ahead and give that the density of water is 1,000 kilograms per meters cubed. Okay, so in this one, we're going to go ahead and need to go ahead and see what we got. So we're going to draw it out. And this one, the best way to kind of draw this one out is if we draw the conical tank with the vertex at 0, 0. So we know that the radius is 10. And we know that the height of it is 20. Okay, so what we have here is we have the mass is equal to the volume times the density. Well, we know what the density is. We know the density of water is 1,000. So what's the area? What's the volume of this cone? Well, if we look at it, all it is just circles packed up onto each other at a height of 20. So we know that the mass is equal to pi r squared times h. So what we can go ahead and then do is that our radius changes. Our radius, every single slice, if we go ahead and dissect this and we go ahead and select the slice, right, this little circle here, in a sense, that looks like it could be a disc, right? Our cross section is just like this with some type of thickness. The thing is, the radius of that, we know that the radius at the top of it is 20. 10. The height of it is 20. But we don't know the radius of what the cross section that we picked out. And the cross section keeps changing. Or sorry, the radius keeps changing. So in a sense, our radius is x as we go up and down the cone. So our mass is equal to pi. Our r, we know that it's going to be x because it's ever changing, which is x squared. And our height, we know our height is going to be, which is basically our thickness of the cross section, it is dy. When I mean by height, I don't mean the height of the actual conical tank itself. This is the volume of the slice, or our cross section. So then what we do is we go ahead and multiply it by our density, which is 1,000. Okay? And we're going to have our mass is equal to pi x squared dy 1,000. Okay? But the issue that we're having so far is that we have a dy with an x in there. We need to go ahead and find a way to manipulate that x and turn it into a y. And well, what's actually causing that radius to go ahead and increase and decrease is this side here. That's what's causing our radius to increase and decrease. So if we can somehow find an equation of that line, we could possibly substitute that for x. Now, we know that there's a point here. I mean, all we really need for to find the equation of a line is point-slope formula. The issue is that we need at least 2 points to go in and find the slope. So we know what this point is here. It's 0, 0. And this point here, we know that this top part has a radius of 10. So our x value is going to be 10. And we know it's as high as 20 meters. So that point there is 10, 20. So if we go ahead and figure out we have 2 points, we can find out what our slope is, which is m equals y2 minus y1 over x2 minus x1. Our slope is 20 minus 0 over 10 minus 0, which equals 2. So then we go ahead and put it into our point-slope formula. I usually always choose 0, 0 as my x1 and y1. It's a lot easier. So we have y minus y1, which is 0, equals m, which is 2, x minus x1, which is 0. So then y equals 2x. So this line here is y equals 2x. So if we know what that is, all we have to do is go ahead and divide it by 2, and then we're going to get that x equals y over 2. So now that we have what our x is, we can go ahead and implement that into here. So x equals y over 2 squared dy times 1,000. So now so far we have everything in respects to y. So that's our mass. So then all we have to go ahead and do is grab what our mass is, and we plug that into the formula of force. This force equals mass times acceleration. Now we know what our mass is. It's pi y over 2 squared dy times 1,000 times acceleration, which is 9.8, which gives us a force that is equal to 2,450 pi y squared dy. All I did was go ahead and multiply and divide it by 2, which gives me 245. I left pi outside, and y squared stays as a y squared, because you have y over 2, which is y squared over 4. And if you go ahead and simplify all that, you get 2,450 pi y squared dy. So now that's our force. Well, it's asking us for the work that needs to be done. So the work equals to force times displacement. So our work is equal to 2,450 pi y squared dy. Our displacement for this cone is that we know that it's being pumped out from a little spout that's 4 meters above it, right? So if we know that from 20 to the vertex is, from the vertex to the top of the conical tank is 20, and we know that it's being pumped from 4 meters above it, that means that we know it's being pumped out of 24. But the thing is, from our, go ahead and pick a different color. From here, we know it's a y value. That means that it's already at a specific position in a y value. So that means it needs to move up to 24. So what is that area that it needs to move further? Well, that area is going to be, or the displacement is going to be 24 minus y. That's going to be how much more that actual specific slice needs to move to get outside of the tank. This is y. So now that we have our work, we're not only looking at that specific slice, we're looking at every single slice that comes above it and below it. So we got to go ahead and integrate that. Well, we're doing it with respect to y. So how low can we choose a slice? Well, we already know that the tank was only about a quarter full. So if we only know that the tank was a quarter full, that means it would never reach, we would never be able to select a slice higher than a quarter. So we know that. So what is 20? 20 is from 0 to 20. That is the total distance of the conical tank, which means that it was fully full. But it wasn't. It was only a quarter full. So a quarter, which is 0.25, if we take 20, which would be a full tank, and we divide it by 0.25, which is a fourth of a tank, or sorry, multiply it, that gives us 5. So that means that the highest that we can slice that we can select from is from 0, from a value of 0 on y to a value of 5. So that means that our A is going to be 0 and our B is going to be 5. Again, the tank was only that much full. If we decide to pick a slice and our slice that we selected was there, we can only select the slice below it, thinly slices, that's what dy is, or above it. We cannot pick a slice higher than that because there is no water there. It was only filled up to 5. So that's why we get our 0 and 5, which this will be our A. The smaller value is usually the A, and this will be our B. So now we just go ahead and fill everything back in. 2, 4, 5 pi y squared dy, displacement of 24 minus y. Okay, and then we go ahead and plug that into our calculator, and we're going to be left with 64,94261.06. I'm leaving it at 2 decimal places. You can go ahead and leave the pi out of it if you want to. I know that makes my life a little easier. In this case, I'm going to go ahead and actually multiply the decimal place, multiply the pi in there to get a decimal place, and I'm going to leave it at 2 decimal places. So that's how much work needs to be done to empty the tank that is 1/4 of the tank full. So these are just some examples that you can go ahead and use. I mean, like I said, multiple tanks can be different types of shapes. There can be, like I said, cylindrical. There can be trapezoid. There can be spherical. You name it. You can think of it any shape that we've come up with. They can probably make a tank out of it. Octagonal can be another one. But these are just two examples. The only difference that's going to really make is how you can go ahead and manipulate your volume to go ahead and utilize that formula to get your mass. Density is always going to probably be the same of 1,000. Acceleration is a constant, which is 9.8. Like I said, your mass, make sure that it's always in some type of actual mass form, which is kilograms, grams, something along those lines. But we'll go ahead and leave it there, and I'll see you guys in the next video.